Okay, so in this video, we are going to discuss one more kinematic synthesis problem. Uh, right, so here, what we're going to do is once again 4-bar mechanism, but it's 3R 1P mechanism, basically a slider crank mechanism. Okay, slider crank mechanism. Okay, so how do we define our requirement? So the requirement is like say I have a simple so this is my slider, okay, and this is my L2, this is my L3, okay, and this point is my O2, that's my A, and let me call this as my B, okay, and the B is going to vary, right? Now my requirement is uh, at one extreme position this is going to be my slider, and another extreme position this is going to be my slider. Let me call this position as B1 and this position as B2, and now my requirement is B2 or B1 minus B2, the distance between those two extreme points is some uh, value, okay, some like 5 centimeter or something like that. So without representing any unit, I'll just put some number 5, okay. So 5 could be 5 centimeter, 5 millimeter. Accordingly, my L1, L2, L3 will also have the same dimension or unit, actually, not dimension. The dimension is always length. Okay, so if this is my requirement, what should I identify? I should identify L2 and L3. I think that's it. And eccentricity, but for simplicity, I'm going to assume the eccentricity to be 0. Okay, fine. Let's see how to perform this, or how to construct uh, such a mechanism which satisfy these requirements using GeoGebra. Okay, so what am I going to do? I am going to create these two extreme points. Let me first construct an extreme point B2 and another extreme point B1. Okay, and I'm going to assume one extreme point which is at the origin, and I'm going to call that point as B2, okay, and another extreme point B1, but I'm going to give that as an input. Okay, so let me call this variable as some S. Okay, so I'm gonna define S which is equal to, say, 5. Okay, so in that case B1 is equal to B2 plus, in the x direction it's 5 and in the y direction it's 0. Okay, so that's my, so this is B2 and that's my B1. Okay, Now what am I going to do? In this picture I'm going to choose the point O2. So I'm going to choose such that so while I choose this point O2, I need to make sure that this point O2 is along the line which connects the point B1 and B2, and we know the line which connects the point B1 and B2 is this x-axis. So I need to choose my O2 in this line, okay, because we have assumed the eccentricity to be 0. Okay, for that reason I'm going to choose my O2 along this line. Let me arbitrarily choose this point, and let me rename it as 2. Okay, so that's my O2. Now what is the other point I need? Okay, this point A1 and A2, right? Okay, so the distance L2, okay, the distance L2 is the distance between point O2 and A, right? And that distance will be half of this distance, the distance between B1 and B2, or half of this S. Okay, so I'm going to define A1, okay, or why don't I define it directly like L2, which is equal to half of B1 and B2, which is S divided by 2. Okay, fine. So that's my L2. And then what's L3? So L3 is equal to, maybe for L3 let me draw the point A1, which is equal to O2 plus yes, comma, sorry, not yes, yes divided by 2, or instead of saying yes divided by 2, let me call that as L2 comma O0. Okay, so that's my A1, and A2 will be in this side, okay, with the same distance. Okay, fine. So in that case, what is L3? L3 is equal to the distance between A1 and B1. Okay, so A1 comma B1. So have I got L2? Yes. L3? Yes. In that case, from this picture, L2 check, L3 check, I have got the configuration. Sorry, I have got the link lens. Okay, so now let me make sure whether my design is correct. So for that, what I'm going to do, I'm going to construct with this L2 and L3, and I'm going to check whether the point B is moving between this B2 and B1. Okay, fine. So for that, I'm going to define A, which is equal to O2 plus L2 into cos even before that I need to define the angle, right? So let me define that angle, which is equal to, right now let me define that as 0. Later it will define it correctly. So A is equal to O2 plus L2 into cos dh into pi by 180 comma sin dh into pi by 180. Right, so let me hide a1 because when theta is 0, a1 will be as same as a. Okay, so now I have got a, and now what's b? So how should I identify b? So in order to identify b, I have to draw a circle with a as a center and L3 as the radius. So let me draw that. So A as a center and L3 as a radius. So now I have that circle, and when that circle intersect with this line, that's going to be my point B. Okay, so for this case, for this, when theta is equal to 0, B is also equal to B1. So what I'm going to do is, let me now hide this B1 and B2. Okay, so this is going to be my point B. Let me check whether I can do that intersection with that circle along with this x-axis. Seems like that. Let me check. Okay, fine. So that's my point B. Now let me connect all these points with the line segment. So between O2 to A is second link, between A and B is my third link. Okay, now I think we have constructed all the configurations. Once again, let me switch on this B1 and B2. Okay, and now in this theta, I'm going to introduce slider, and I'm going to give a setting with 0 is the minimum and 360 is the maximum, but this is increasing. Okay, fine. Now let me hide the circle. Okay, yeah. So now if you notice, we have constructed a slider crank mechanism with a desired stroke length. So that's why we call stroke. Yes, is the stroke length. Okay, so is this the only is the solution unique? The answer is no. What you can do is you can change the position of O2. Okay, so you can change the position of O2 accordingly. The link length, particularly the link length of this L3 will change. Okay, so that's one of the simplest kinematic synthesis of the slider crank mechanism. Thank you.